Hi, I'm Shui Yang. I'm from the Department of Electronic Engineering, the Chinese University of Hong Kong. This paper is about building a speech emotion recognition system, which enables deep learning models to focus on the emotion salient parts of a speech. And this is achieved using attention-based modeling. Our task is speech emotion classification based on acoustic features. Given an input emotional speech utterance, the output is a single label of emotion type. Speech emotion classification at utterance level can be formulated as a sequence to label problem. The input utterance is divided into a sequence of speech segments, and the output is an utterance level label. In general, most of existing emotional corpora are weakly labeled. In other words, they do not give segment-level labels. To learn segment embeddings without segment-level labels, this paper proposed multiple instance learning to train a segment-level model, and it is trained in a weakly supervised manner. Furthermore, for a sufficiently long utterance, not every segment contains relevant emotional information. Therefore, this work investigated 3 attention-based modeling to make the network focus on the most emotion salient parts of a speech. This figure shows an overview of the proposed method. It comprises a convolutional network to learn segment embeddings. The acoustic features are log-Mill feedbacks. The segment embeddings are then used as inputs for utterance-level emotion classification, and this is achieved by a dense layer network implemented with various attention mechanisms. This figure shows an example of segment-level predictions generated by a convolutional network for a speech file from the CISA corpus. The horizontal axis represents the segment index, and the vertical axis is the segment-level predictions. We can see that the segment-level predictions change across the utterance, and not every segment contains relevant emotional information. If we can place additional focus on these more relevant segments, system performance would be improved. In this regard, we investigated 3 attention-based networks. They are decision-level single attention network, decision-level multiple attention network, and the feature-level attention network. The attention networks construct the utterance-level prediction as a weighted sum of the segment-level predictions, and those more relevant segments are expected to be assigned with larger weights. For the decision-level single attention, the utterance-level prediction is the weighted sum of the segment-level predictions, and the weights are learned by an attention function omega, as seen in this figure. The decision-level multiple attention is an extension of the previous decision-level single attention. It consists of several single attention modules that are applied to intermediate layers. The outputs of these attention modules are then concatenated to form the utterance level representation. In this work, we use 2 single attention modules to form the multiple attention model, as shown in this figure. For the feature level attention, the utterance level representation is first modeled as the weighted sum of the segment level bottleneck features. In this formula, Q represents the bottleneck features and V is the weights. Note that D denotes the dth dimension of the bottleneck features, and it can be any value. This diagram summarizes the whole system. Segment embeddings are first learned by convolutional network from log-field banks. Then the segment embeddings are used as input to the attention-based networks to make the utterance level decision. Four multiple instance learning-based baseline systems were built. The first baseline is maxed-out segment embedding, where a maxed-out pooling is directly applied to the segments. The second is averaging segment embedding, where an average pooling is directly applied on the segment embedding. Next is the maxed-out pooling baseline, where the maxed-out pooling is applied on the segment level predictions. The last is the averaging pooling baseline, where the average pooling is applied on the segment level predictions. Two popular emotion corpora are used to evaluate our method. They are CISA corpus and the MOCAP database. And this figure shows the distribution of speech file duration for the CISA corpus and the MOCAP database, respectively. And the average duration for CISA is 2.07 seconds, and it is 4.55 seconds for MOCAP database. Since the input for our attention-based networks has to be equal for all speech files, we heuristically set the fixed length for each speech utterance to the average duration of each dataset. Longer speech utterances are cut at the fixed length, and the shorter utterances are padded with zeros. In our experiment, the size of each speech segment is set to 335 milliseconds, and the hop length is set to 60 milliseconds. The architecture of the convolutional model is similar to the SEC-CNN model as used in our previous work. The only change we made was to the last three fully connected layers. In the training stage, Adam optimizer with default setting in TensorFlow carries was used. With an initial learning rate of 0.001 and an exponential decay rate of 0.8 every 2 epochs, the batch size was set to 128, and the early stopping with patience of 3 epochs was utilized to mitigate an overfitting problem. For the CISA corpus, the segment embeddings are generated using leave one fold out, 10-fold cross-validation. For the MOCAP database, the segment embedding are generated using leave one session out, 5-fold cross-validation. When apply the attention networks to the segment embeddings, a second cross-validation is performed, and the results are presented in terms of unweighted accuracy. This table shows the experimental results on the two emotional corpora. The first 2 lines shows the result obtained by 4 baseline systems. They are maxed out segment embedding, average segment embedding, maxed out pooling, and average pooling, respectively. We can see that our baseline systems have already achieved respectable results. This proves the effectiveness of the multiple instance learning-based framework for extracting the segment embeddings. And the last 3 lines show the results obtained using 3 attention-based networks. It can be observed that the attention-based modeling substantially augmented the performance of the baseline systems overall. And this table compares the decision level single attention and the decision level multiple attention modeling. Due to the positive combination of different attention modules, the decision level multiple attention outperformed the decision level single attention modeling. We can also see that the feature-level attention modeling achieved better results than the decision-level attention networks. This is because the dimension of segment-level features in the attention network can be any value, but the dimension of segment-level decisions is fixed to be the number of emotion classes. With such increase in the dimension, the capacity of feature-level attention networks is increased. This table compares our system with other competitive methods. We can see that our performance is among the state-of-the-art on both emotional corpora. This work improves the multiple instance learning-based speech-emotion classification by attention-based modeling, and the 3 attention-based networks are investigated. We achieved the state-of-the-art performance on 2 popular emotional corpora with the proposed method. Since in this paper, we blindly used all segments to train the segment-level network, it is anticipated that with proper segment selection strategy, better results are expected. Also, more advanced network architectures and better algorithm optimization will also be explored in the near future. So that's all for this video. Thanks for your attention.